So the rest of the talk involves a post A star word. What is going on? So you don't need to go through it in great detail. There is one key aspect that I want to highlight, which is that what happens when A star discovers a change in the environment. So if A star discovers a change, remember over here we assume the whole map was known, except that the robot is not able to see it, right? That's not change in the environment. So a change in the environment is if you're working on this map, that squares red and blue, and then suddenly there is a blockage in a different location. Then A star, it can still plan, but what has to do is you have to rerun A star. So every time you see something different from what you expect, you will have to rerun A star. So that was the only weakness of A star, because you have to rerun the whole program. Basically shut down and rerun the whole program from wherever the robot is, and it spotted a change in the map.
So like basically through backtracking you have to go to the last square where there is no obstacle and rerun A star.
No, you can run it from the first square where you saw an obstacle.
Yeah.
From that point on you can run it.
Yeah.
But you have rerunning means clear all the, the most important things are the F, G, H values.
Yeah.
You got them all stored, right? But now when you clear the program, from that point onwards you have to again generate, F, G and H values.
Again the master load should be calculated.
Huh?
Again the master load should be calculated.
Yeah, right. And that's, so somebody, there was a group that came up with an algorithm called D star light. So they figured out that you can save the cell values. You don't have to shut down the program, but when you see an obstacle, what happens is certain values need to be repaired. And they found out that the whole environment does not need to change. You don't need to repair the cell values everywhere. They came up with an algorithm where if they spot an obstacle in a place where they thought there was nothing, they can just repair a few cells. I'll give you an example. It will show how clever those people are, because they figured out that maybe 10-15 cells, it changes based on the situation, just need to have modified cell values. And then you can continue with the algorithm from that point onwards. You don't have to shut down the program and run it again. So here's the thing. Both D star light and A star will give you the same path, but D star light will run faster than A star because it's not shutting down and restarting. So we're going to jump to that part because these are details that you'll never remember anyway. Here it is. So this is from a paper, original paper, D star light, from Carnegie Mellon, I think it is, S. Kenning and Higashire. So the values you see here, these numbers, are not needed to be calculated. The reason he's putting the goal distance from all the cells, the goal distance, where is the goal? Goal is here, right?
Yeah.
So you see 1, 1, remember that? 2, 2, 2, it's like a brush fire. So that is being added so that he can point out why D star light is efficient. That's the only reason. You don't need to calculate those. Alright, so this is the knowledge before the first move of the robot. So robot started here, it was told to go here, right? So it figured out a path, and the path goes right up to here. It thought it can go through this gap. But guess what? When it came here, it discovered there's a tree that has fallen across the road. So now A star would say, clear everything, start again, right? So what this guy found out is that, first of all, think of it, this is very logical. Because if the blockage is here, why would the goal distances of all those cells need to be changed? They don't have to be changed.
Yeah.
Only the goal distances behind you, if at all, need to be changed, right? So only these goal distances need to be changed. Except that, do we even care about all those cells behind us? Why do we care about cells that are behind us are not going to be part of our path? So let's read this. Robot moves and discovers blocked cell on path. Cells with altered goal distance is shown, gray. Majority not relevant for new path. So the majority of these are not even relevant. So A star doesn't even care about this. It clears and starts again.
Yeah.
But what he pointed out was only these gray cells, right, which is a small fraction of the whole environment, needs to be changed. And not only that, the majority are not even relevant for the new path. So this cell would not be relevant. Right? So D star light efficiency is because it identifies those cells that have changed and are relevant to the replanning task. So those turn out to be just a few around here. So he's got an algorithm. He's not just showing an example and saying, oh, that's relevant. He's got an algorithm to pick out the cells that need to be modified. So he can just repair those cells, not shut down the program, and then find a new path. And look, the new path makes sense because you just go around the blockage. So A star would close down the whole program and start all over again. It will take more time. But D star light, it keeps the program alive and repairs those very few cells. So I'm going to show you some research results. The contrast of the picture is poor because of the projector. So this is the central area that I was trying to describe to you inside our building, where some work can go on even during winter. So you can see, there's my mouse, here it is. So we created a zigzag course. So we were doing some work for the army. From that YouTube video I showed, that the zigzag course is the one that stresses out both D star light and A star the most.
Yeah.
Because the cells, you're going to read more and more cells. So we were basically comparing A star and D star light. And in order to make D star light work a lot, right?
Yeah.
And A star work a lot, we have to block the path except for a tiny opening on the right, tiny opening on the left. So that's what a zigzag course is. So everything is blocked here except for a hole here, and so on. That's why it's called zigzag. And then we also introduced a surprise obstacle. I think the robot is starting here and ending up here. We created a surprise obstacle. You know what a surprise obstacle is? The map was known except for these two barrels. And we are able to then figure out how much time the algorithm takes to process that new obstacle on the map. So we basically figured out, what does A star do? A star shuts down and starts again. So we know the time for that. D star light, it modifies and repairs those cells. So we're able to compare and show that D star light is a significant improvement over A star light. So it is a very carefully constructed surgical environment. So we had to create the map for the whole thing, and then we had to create 2 extra barrels. So you know what the difference is? That is early in the run. That first surprise barrel, it basically says surprise barrel, that is closer to the beginning. This one is closer to the end. So we wanted to, because if you're closer to the end, there'll be very little time taken, because all the cells are directly in front of you. If you're closer to the start, then there's more cells involved in the repairing, right? You know what I mean?
Yeah.
So that's the scene, and that's the study you see here. So the zigzag course is the best stress test for A star or D star light. And this is we didn't have ROS at the time. This was almost like 12 years ago. ROS was just then starting. We had its father, player stage. So player stage was the precursor to ROS. And the same guys who worked on player stage worked on ROS 1, and now they're working on ROS 2. So there are 2 scenarios we created. One with map known, and one with map unknown. Except that this one doesn't show that. I think on the very first day when I gave you the introductory talk, it had mapped and mapless travel.
Yeah.
This one is just looking at the surprise barrels here, right? Surprise obstacles in your road. And there it is, yeah. That original figure is back here. You see, when you don't know the map, you're going to go right up to the... So you're not going to go like the bug algorithms, right? They went right to the wall and touched it. You don't have to do that, because at some point, based on your LiDAR range, you'll see it. And then you go along the phase and then get in here. But if you have a map, then you don't even do that. You just go directly for the gaps. Yeah, a quick look at the random tree. So for that, so I included another Brian Douglas video here, because I'm a big fan of the guy. So he explains A star and RRT in his own way. But I don't know, maybe we can do this. We can do Brian Douglas instead of the other one. And then we'll switch to...
In the last video, we covered simultaneous localization.
So this is a follow-up to the postgraph video.
We ended up with a map of the environment in the form of a binary occupancy grid. Now, for this video, we're going to explore some of the ways that we can use a map like this for motion planning. That is, finding a trajectory through the environment that connects a robot's starting state to some goal state. And we're going to briefly cover what motion planning means and how we can use a graph to solve this planning problem. And then we're going to cover 2 popular approaches for creating that graph: search-based algorithms like A star and sampling-based
Those are the
algorithms
two
like
categories.
RRT and RRT star. And I think this video will sort of nicely set a base understanding of how we can use graphs to plan a trajectory through a known environment. And it's something on which you can build when you go out and learn more about these planning methods. So I hope you stick around for it. I'm Brian, and welcome to a MATLAB Tech Talk. We want to find a path from a starting pose to a goal pose. And if we're talking about a robot that moves along the ground, there may be three states that make up its pose: X and Y location and its orientation. A path is a sequence of pose states that smoothly connect the start and the goal. And determining this sequence is called path planning. Now, path planning is just a subset of the larger motion planning problem. With motion planning, we're not just concerned with the sequence of poses, but also their derivatives like velocity, acceleration, rotation rate, and so on. So with motion planning, we're trying to dictate precisely how the robot moves through the environment. With path planning, we're just concerned with the path that it takes and not how fast it accelerates or moves through it. Of course, the size of the pose vector depends on the specifics of your system and environment. Instead of three states, it could be just two, X and Y, if the robot is omnidirectional and orientation doesn't matter. Or in the case of a robotic arm with multiple actuators, the pose could consist of dozens of states. Now for this video, the examples I'm going to use focus on path planning, and for a robot that is omnidirectional, so just two pose states. This will simplify the explanation, and hopefully you'll be able to see that these techniques can be extrapolated to higher dimensional systems. All right, let's get started with a simple map that's similar to the one that we generated in the last.
One of the things I found in watching others describe something that you're interested in, but you think you know, is a different perspective, sort of, gives you a different angle on the same problem. So he described A star, which we've already discussed but let's listen to his
just a rectangle
version of it.
And assume that the starting pose is up here and the goal pose is over here. A minimum distance solution can be solved for directly by connecting the start and the goal with a straight line, as long as there's no obstacles in the way. Now, if the robot moves along this path, it's going to reach the goal in the shortest distance possible. Now, analytically solving for the shortest path like this is trivial for our simple environment. And this type of solution can even work for environments with some obstacles and constraints as well. But for many problems, the obstacles and the dynamics of the system are too complex to generate an optimal solution analytically. So we approach it by solving the problem numerically. And as I said at the beginning of this video, we're going to focus on graph-based methods to numerically find the path with the shortest length. Before we get into any particular algorithm, let me show you the general idea behind graph-based solutions with this simple map. Graph-based algorithms work by discretizing the environment. That is, breaking it up into discrete points or nodes, and then finding the shortest distance to the goal, considering only these nodes. Let's approach this problem in a random way. The starting location is the first node in our graph, and it has a cost of 0 since we're already there. So I'll put a 0 inside the node. Then we can move in a random direction and place a node in the graph at our new location. The edge between the nodes is how far we travel.
So he's going to show you that a plan that you might conceive that is common sense, right, may provide a solution, but you won't necessarily get the best solution. And then he's using that to push you towards A star. He's saying that A star is basically an organized way of doing something that you do anyway, except that you will not come up with an optimal result, right? And watch how he builds it up.
And the cost of getting to this node is the length of that one edge. Now we take another step in a completely random direction. Place another edge, and the cost of this node is the total of 3 units. And we can continue to do this on sort of a random walk until we get to the goal. And the cost of this particular random path is 10 units. We've found a path that works, even though it's definitely not the shortest path. So we can start again, taking a new random step and adding a node and connecting it with an edge and recording its cost. And if we happen to reach a node that we visited before, we can compare the cost between the two different paths that we took to reach it and keep the smallest one.
And we kind of did that.
Yeah.
Because once you have two paths to the same node, it makes no sense to keep both of them, right? So you have to eliminate one which is worse. And that's what he's doing here, because the cost is 2 plus 1 plus 2, 5 versus 2 plus 1 plus 1 plus 2, 6. So that's intuitive, but human intuition has to be supplemented by man to get an optimal result.
Basically, we're revising our estimate on how many
He
units
changes
it
all
takes
estimates
to
based on
reach
that.
that particular node. We now have this graph of nodes or locations on a map and how much it costs to get to each node. But we should recognize here that we don't actually need to build a fully interconnected graph, just a tree, which is a subset of a graph. A graph can have nodes connected in any way you want, but in a tree, each node only has a single parent. If you can get to a node two different ways,
This node has two parents. Not good in path planning. So he says, do
it
not
doesn't
keep
make
the other
sense
one.
to keep the path that is longer if you're looking for the shortest path. So you can remove the edge for the longer path, keeping a tree structure. In this way, a tree would start at the location of the robot, and the branches would venture out to other states but never recombine. Now, to find a shorter distance to the goal, we can just keep randomly wandering the environment, updating the tree until we find a branch that gets to the goal with a cost that is low enough. It doesn't guarantee an optimal path, but it will continue to approach optimal as the number of nodes go to infinity. Of course, building up a tree through random wandering is not the best solution. So this is where path planning algorithms come in.
So what he has described is the basis of the RRT method, the sampling based method,
Yeah.
but he's making an argument. He's not saying that RRT is useless, right? But he's saying that if you don't have enough samples, you end up with a suboptimal result. And so why not do it with A-star? Or if you want to use RRT, use a lot of samples. So it's kind of nice. He's got both covered, the random methods as well as the deterministic methods.
They provide more efficient ways to build this tree. I want to start with the so-called search-based methods that build up the tree by adding nodes in an ordered pattern. And one way to accomplish this in practice is to start with a grid-based map, like the occupancy grid that we have, and go cell by cell and determine the cost or the distance the robot would have to go
So that was the
in
method we
order to
discussed,
reach
A-star.
that cell. Here I'm claiming adjacent moves are 10 units and diagonal moves are 14. Now this is similar to the random approach that we just did, except we're methodically working our way through each cell, calculating the cost to reach it, and if it's the shortest path to that node, then we update the cost and a tree to reflect it. And once we've covered every single cell in the grid, the optimal path is simply the sequence of cells that produce the minimum cost at the goal. This will produce an optimal solution, at least optimal at the resolution of the grid. But you can see that it would be computationally expensive since it's kind of a brute force method of checking every possible node. So to improve this, researchers came up with the A-star algorithm. This was in 1968 to give Shaky the robot the ability to determine where to go on its own, which was a first for general purpose mobile robots. This search-based method still adds nodes in an ordered way, but it does so by prioritizing the nodes that are more likely to produce the optimal path and searching there first. It does this by keeping track of some other heuristic, like the straight line distance from the node to the goal, in addition to the cost of the node. And the sum of these two numbers is the absolute minimum cost of the path.
That's the heuristic.
If there was a straight line shot to the goal, then you can imagine how the total path length for, say, this node would be 48. We've already gone 10 units, and we have a minimum of 38 left to go. Therefore, this other node should be prioritized, even though its current cost is 14, since there is the potential of only having 28 more units to go for a total of 42. It makes sense to keep trying this path. So in this way, A-star allows us to search through the nodes in a way that will get us to the goal without necessarily having to add every node into our tree. In fact, once we get to the goal, we know that we took the optimal path, since every other path would have a cost plus distance to go that is greater than the path that we found. Now, this was a fast introduction to A*, and I was going to make an animation that shows how this still works in the presence of obstacles, but honestly, I couldn't do better than what Sebastian Lemieux already has on his YouTube channel. Which
That's one of the references I had. Yeah.
His video and animation on A* is amazing, and I recommend you check it out if you'd like to know more about this method. Alright, so search-based algorithms give us a way to build up a tree by adding nodes in some kind of an ordered pattern. But one problem with these types of algorithms, even efficient ones like A*, is that they become very computationally expensive as the size and dimensions of the state space increases. You can imagine how the number of grid points grow exponentially as the number of dimensions increase, which can slow everything down. So they tend to not be used for high-dimensional state spaces, things like determining the path for multi-jointed robot manipulators, or for really large, low-dimensional state.
You realize that? When you have the traditional robot manipulators, right? So I told you, the one arm has something like 22 degrees of freedom. Now, you don't give fingers to all the robots on the assembly line, but they still have a lot of degrees of freedom. You know, maybe 7, 8, 12, something like that, right? Because, you know, rotation, pickup, you know. So that problem is actually running in 12-dimensional space. For robots, it's x, y, theta, right? It's not even theta because the A* ignores theta. If you want theta included, then remember the first video I showed you today where he's taking into account a regular car. So then the dimension becomes 3 in planar space. If it's a drone, it becomes 6. 6 is still controllable, right? But when you have those manipulators, you can have like 12-degree space, and they still use A* to figure out the best path. The path is now this, right? Go underneath the table and pick up something and put it here, kind of thing. That's the path now. So.
Bases, ones that might have millions or more grid cells. This is where the so-called sampling-based algorithms are useful. To understand how sampling-based algorithms work, I think it's first helpful to realize that in our map, and probably most maps, there are sections where a path could continue in a straight direction for some distance before it needs to make a turn. With A*, we have to calculate every single grid cell between these 2 points, so multiple nodes in the tree. However, if we only checked the far distant node and there weren't any obstacles in the way, then we could calculate the straight line cost for just this one node. This reduces the total number of nodes and therefore the total number of calculations. So the question becomes, how do we pick the location of these sparse nodes so that we still reach the goal? And one answer is to randomly select them or sample them, hence the name. Now, I know I said that randomly selecting nodes is not the best approach to build out a tree, but we're going to choose a random node location a little bit differently. Rather than extending the path through some kind of random walk, which could allow the path to circle back on itself and take a long time to explore in the direction of the goal, we're going to be smarter about randomization and focus on rapidly exploring random trees.
So you got it?
Yeah.
Total randomness is like brainless. Because you're going back there and the goal is here. So he's saying that the RRT, rapidly exploring random tree, rapidly exploring is what I think the creator got her PhD thesis or his PhD thesis on that topic, on the RRT. So basically you're going to force it towards the goal somehow.
RRT, and a version of it that can approach an optimal solution called RRT*. Let's go into how the basic RRT algorithm works. From the starting node, we need to place a new node in our tree. And RRT does this by randomly selecting a node anywhere in the state space. And once we have this random node, we want to connect it to the nearest node in our tree, which, since we're just starting, is the first node. But we don't want to place it too far away, because the chance of the path crossing an obstacle or just traveling too far in the wrong direction is greater with a longer edge. So we specify a maximum distance that the new node should be away from the nearest node.
Maximum distance.
Now, a quick aside, if the random node is closer than the max distance, then we just place the new node right there. Also, if there's an obstacle between the nearest node and where we want to place the new node, then that one's just ignored completely. Nothing is added to the tree, and we move on. This keeps the tree from attempting to cross through any walls or other obstacles. Okay, let's move on. We randomly select a new node and find which existing node it's nearest to. Again, this happens to be the starting node. So we already have two paths in our tree, and both are venturing out into different parts of the state space. A new random node, and again we connect it to the nearest, which is growing one path even further into the open space. This is why the algorithm is called rapidly exploring random trees. When there are large unexplored areas, like we have, then there's going to be a good chance that a random node is selected in that area. And this has the effect of adding new nodes in places that cause the paths to venture into unexplored areas quickly at the beginning, hence rapidly exploring. And a random node that is in a direction opposite of the goal doesn't affect the path that's on its way to the goal, since a different node would be nearest. In this way, one path is always rapidly making its way towards the goal, and the others are rapidly making their way into other open areas of the state space. And then later on, as the unexplored area starts to fill up, the random node selection tends to just fill the tree out with more branches. Now we can continue doing this process until the path gets to within some threshold of the goal. At that point, we have a viable path, albeit probably not an optimal one, since this method tends to zigzag as it makes its way. But we did find a solution, and importantly, a solution that is likely using fewer nodes than would have been necessary for A star, since the nodes can be spaced further apart. Again, we set that with the maximum connection distance. Now, RRT can work really well for situations where you're just looking for a valid path and not necessarily the shortest distance. As long as the start and goal nodes are reachable, this method is guaranteed to find a path as the number of samples approach infinity, and in most cases, a much, much smaller finite number of samples. Now, if we do want a solution that's closer to optimal, we have to add some additional steps into the RRT algorithm, and we get RRT star. For RRT star, the node selection process is exactly the same. We choose a random node, find the nearest neighbor, and if there's no obstacle in the way, we place a new node at the random node or at the max connection distance, whichever is smaller. The difference, however, comes from where we connect this node to the existing tree. We don't necessarily connect it to the nearest node. Instead, we check for other nodes within some specified search radius and determine if we can reconnect these local nodes in a way that maintains the tree structure, but also minimizes the total path length. So here, I'm connecting it to this other node, since that's going to produce a shorter path back to the start. Let's watch RRT star work with a slightly more complex environment. Here, I'm using MATLAB to do the visualization and the RRT star function from the navigation toolbox. At the beginning, you can see that it's rapidly exploring the environment, and doing so with just a couple dozen nodes. So far, it's not different than RRT, but let me pause it right here. This next node is going to appear here. If this was RRT, it would connect that node to this one, since it's nearest. But watch what happens. That node appears and it's connected all the way down here, since that's a shorter path back to the start. And it reconnected some of the other nodes within the search radius. So RRT star is always trying to shorten the paths. Let's continue. Here it reaches the goal, and just like with RRT, the path is a bit zigzaggy at first. But as we continue adding more nodes, and the existing paths are reconnected, you can see how they get refined over time, becoming shorter and straighter. We can stop adding nodes whenever we're happy with the result.
So the beauty is, or the key aspect is, you've got to know when to stop. And when you do get to that point, you may still not have the path generated by A star, but it's okay. I told you, in practice, you have all kinds of other things like friction of the wheels and so coming into the picture. So it may not be that different. We always think of this, okay, this is a perfect path, I've got to get there or else I failed, right? But But in practice, you have many other issues in the real world, with the tires on the ground and slippage and so on, bad localization, etc., etc. So at some point, you can stop. And why is it faster? Because the number of nodes explored is still smaller than A star. That's, you got to stop there, because if you're going to go all the way and create like 1,000,000 nodes or infinity, as he says that infinity will give you the perfect path, then you lost the battle, because you might as well have done it through A star. The other thing I'm going to point out is that the kinematics and dynamics, for a long time I was wondering how do they do trajectory planning, right? Because he kept talking about path planning, but they're not talking about how to take a vehicle through that. Apparently these RRT paths are refined enough so that you can let the vehicle navigate the corner point. So basically you'll find enough curvature here and here so that most robots will be able to go through without having a problem. So it turns out that you don't need that trajectory planning aspect most of the time. Sometimes you may, if you have a long 18-wheel truck, then it's a different issue. But for most cars, it can navigate this path. So I've rarely found a trajectory planning approach. Typically a trajectory planning approach is attached to an A star path, because it's like this. But here it smoothens it out, because it's not wasting a lot of cells in other places. Most of the cells are focused on the areas connecting the start and goal points around obstacles. So you really have to try it out to accept that, right? I've never tried RRT. I watched these animations in MATLAB, but I never tried it myself. When you try it, you'll get the confidence that it's can be as good as A star, or better because it's quicker, right? Better not from the point of view of the path, but better because it's quicker. Remember, quicker is also important in many applications. All right, so that's the end of the. There are some other videos you can go take a look. Here is another animation of RRT star, something called random trees. You can go look at it later, and basically more stuff that you can watch. So, last topic coming up. So I did upload the 2 files. So sensing is boring. Perception is interesting, right? Sensing is, I got a sensor that gives me this raw data. Perception is where you can be very creative. So we'll start with sensing. Robot sensing is the name of the topic. Somewhere here you'll see some former VIT students. So these are the core robot sensors. Just a listing. Maybe modern robots have some more exotic sensors like torque sensors and so on. But basically wheel encoders, we kind of went through this when we did odometry. LiDAR and ultrasound, I put them in a category because they both tell you the distances to obstacles. These are active ranging. Active ranging is you throw out some energy and you get it back, right? They can also be ranging where it's passive. The cameras can be used as to find the distances to obstacles. They are passive because you're not throwing energy at the obstacles. Compass provides heading. A GPS sensor produces or reports absolute positioning. A gyroscope is related to rotational motion. It gives you the angular rotation rate, d theta by dt. And then by integrating it once, you can figure out the orientation. Just like accelerometers can be double integrated to get XYZ, then gyroscope can be integrated, the angular rotation rate will be integrated to end up with the angle. We already talked about accelerometers. And it's possible to get the force also. What is the force causing motion in this direction, this direction, and this direction? Because when you get acceleration, F is equal to ma. So you can figure it out. Now it gets more interesting because there is this IMU, inertial measurement unit, which is a packaging of, so these are like not new sensors, but it's a packaging of the accelerometer, which we already listed, and the gyroscope, plus the magnetometer. So the magnetometer is measuring the Earth's magnetic field. So that is used to get a sense of orientation, because there is a magnetic field running on the Earth, and if you can sense that, then you can figure out your orientation roughly.
How is it better than just using a compass?
Huh?
How is it better than just using a compass? compass like these two are used for heading.
Well, the compass is also based on that, yeah.
So what's
Unless it's based on a different principle. If you're using magnetic compass, then it is looking at the field, yeah.
what's the like, how is it better? How is the magnetic?
No, better is you have to look at the spec sheet of the of the sensor, and better will only be judged by numbers. So right now we're just identifying the physics that goes into different sensors. So they have the capability of measuring that. Which is better? Then you have to. Now I can say one thing: LiDAR is definitely better than ultrasound, right? But better from what point of view? Accuracy is good, but cost is high, right? So somebody might say, no, LiDAR is not better than ultrasound because I don't have more than $30. So it's all a question of what you want for a particular application. Okay, and then vision sensors, like cameras of various types. Optical is also infrared, it's based on the heat of the body. Optical is just light that is ambient, it's not an active sensor. So these are not active sensors, they're just picking up the energy around them. And now it gets even more complicated, hybrid sensing systems. So we have something known as an INS, which is not exactly the same as the IMU. So the IMU just packages the sensors together, and it's up to you what you do with it. But notice what the INS does. It's a built-in sensor fusion is there. There's a cabin filter already there, and you can bundle IMU and GPS to provide an integrated result. So that is a big convenience for many people. They don't want to write cabin filtering code or do the sensor fusion themselves. So it's ready to go. There's also something known as the AHRS, the Attitude Heading Reference System. So here you have the IMU plus the GPS, but no sensor fusion. Now the reason they do that is they want the customer to make a choice based on how much money they have. If sensor fusion is included, that unit is going to be costlier. If you want to just take the signals and do your own fusion, right? You have excellent software guys, or you already have the package, then the cost goes down. Or maybe they have done it for you, but you're not happy with their particular implementation of cabin filtering. You want to do something much more exceptional, right? Then you want the raw signals. You don't want the software locking you into an option. So that relates to the question you asked, right? When you actually buy these sensors or practical system, you would be amazed how much time you really have to spend. You have to sit and look at the data sheets, and some of the terms, the way they describe the error and the various conditions is ununderstandable. So you often have to call the company and try to figure out what does he mean by this particular thing, and he's given two degrees. What exactly, can you sketch what exactly is his error, right? What does this 2-degree error mean, right? So because it's not a standard terminology. Manufacturers make up their own, and so it's like sitting and researching it to figure out. I'm talking about when you buy something for $15,000, then you'll do that. If you're putting something together for a hobby robot, you're just going to grab the first thing that works. Is that clear?
Yeah.
So when you buy something for $15,000, we had a $15,000 IMU gifted to us. I may have told the other class, but it was a. You can't open it if you're a foreigner. It was there's a name attached to those devices. It's so highly protected that if you have foreign students, they can't be allowed to work on it, and you have to lock it up at night in a secure place. So it was free. They gave it to us free. $15,000 was the cost if somebody else wants to buy it, and it was so sophisticated that the first year we got it, it was just sitting there. So this is another example of something that somebody gives you free, but you can't use it, and it's sitting there in a corner because nobody had the time to figure out how to use it. So an inertial navigation system is a navigation device that uses a computer, motion sensors, and rotation sensors to continuously calculate by dead reckoning the position, orientation, and velocity. So if you tell a boat captain, hey, write some cabin filter code, I'll give you something cheaper, and you have an attitude heading reference system, he's going to say, I can't go back to college anymore. Just give me something that works, right? Every boat has this, by the way. Like boating is a big thing there. Every boat has this. So he's going to want to go for an AHRS, though there are a lot of commonalities between this and that. It depends on how much ability you have to write software of your own. So if everything is integrated, it's going to cost you a lot. Okay, so I've given you a lot of references because this is just a jump off point to, again, Professor Chris Clark's notes. We saw that on the motion modeling. So he's got another set of notes on sensors. Now, you're in a sensing group basically, right? So some of this I'll skip because it's standard stuff. I just want to point out the common sensors that are used in robotics. Not to go through things like what is the precision, definition of precision of a sensor, right? Or the accuracy. So precision and accuracy are not the same thing. People think precision is the same as accuracy. It's not. Okay. So I won't go through that because maybe in one of your classes you may have encountered that. So let's go to the Chris Clark presentation. Well, yeah, we might be able to finish perception. Things are looking good. So about 10 to 15 minutes on this topic, and then we go to perception. You'll see some of your former students in that description. So we've seen this many times. This is how a robot operates. Localize, give some commands, move the robot, then look at the surroundings and localize yourself again and over and over and over again. So this was the robot that one of the videos mentioned again. This is supposedly a classic robot. Maybe I should get the name of the robot and put it here. But look at it. Look at this light. It looks like a huge stone.
Yeah.
So this was like 30, 40 years ago, I'm sure, maybe 50 years ago. So it has an IMU, an emergency stop button right there, wheel encoders, bumper. So they also had a bumper for emergency use, a laser range scanner, this huge device, sonar sensors, planted camera, and an omnidirectional camera. So they have two cameras.
Yeah.
So a lot of software to make sense out of these multiple things. So he's using this to inspire his class. Basically it's about sensors, but he's saying, look, this robot has all of these. So we're just going to do an overview and some examples. Not sensor characteristics we won't go into. So this, I didn't know what these words were like 25 years ago. So sensors are broken down into two categories. One of them is known as proprioceptive and the other is known as exteroceptive. Quite simply, a sensor on a robot that is looking at the outside world is known as exteroceptive. So GPS is looking at the outside world, right? LiDAR is looking at the outside world. So you're saying, aren't they all exteroceptive? No. Odometry, right, is looking at yourself. When you're measuring wheel odometry or you're measuring your velocity, it's all measurements of the robot. So measurement of the surroundings would be done by exteroceptive sensors. Measurement of oneself, the counting steps, is interoceptive. You're looking at yourself. If you look around, remember the second part of Kalman filtering, you look up, that's extero. You point a camera or LiDAR or something else. So that's all it is. It's obviously inspiring them again and pointing to which are the exteroceptive and which are the interoceptives. Okay, there's also a category, there's a categorization of passive and active sensors. I already gave you examples. An optical camera is a passive sensor, a LiDAR is an active sensor. And here he has a pretty comprehensive list. Tactile sensors like contact switches, extero or proprio, exterior, because you're touching the world, contact sensors, right? It cannot be interior. Is it active or passive? No, it's passive. So it's a nice test because I told you, I like structure, like the world has to be structured for us to understand it. If you just lay it out in a straight line, very difficult. Put them in categories is better for us to understand. So that's what it is. Quite a long list. Okay, and you probably being, in the sensing group that you are, you know that resolution is kind of important. What is the difference between one measurement and the next, right?
Yeah.
So as well as range, like infrared range sensors go between 10 and 80 centimeters. LiDAR can go for 80 meters. So big difference. And then there's the dynamic range. What is the ratio of the upper limit of the measurement to the lower limit? So can it measure up to 5 centimeters? So even LiDAR becomes blind. If you get too close to a LiDAR, it cannot see you. So maybe you can sneak in from the side and it's not able to see you. So there is a minimum range. Even the 30-3 LiDAR, go look it up. In that Robotics web page, it has a inner limit. Anything closer than that, you won't see. So how will anybody get closer than that? Only if they come from the side, right? But because if you see them here, they'll have to get to you before you get into that, inner range. So that's what the dynamic range is. Sonar is only 24.8 dB. They always express it as 10 times because the upper limit could be several times, the lower limit. So they convert it to a log scale. They haven't given us a number for the LiDAR, but for the sonar, it's only 24.8 dB. 3 meters and 0.01, 1 centimeter. You can't see within 1 centimeter. Okay, linearity, we'll skip that. No, we don't want that. This is kind of nice. So sonar takes a long time to get a return signal because it's using sound.
Yeah.
So sound is being bounced off an obstacle and collected, right?
Mm-hmm.
And sound, the speed of sound is different from the speed of light. So that's one of the problems. I said there's also a problem of resolution because the sonar is only going to say there's something here. It could be here, 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 but something like 2 meters away could be anywhere in this cone, whereas the LiDAR cone is like this, 1 degree apart for the turtle board LiDAR.
Yeah.
So it's, of course, if you expand this 1 degree out, then you can't tell the difference, right?
Yeah.
If the 1 degree goes out 80 meters, then now again it's behaving like the ultrasound sensor. But nobody makes decisions on something 80 meters away, right? You're just worried about something ahead of you. So from that point of view, a LiDAR is better than a sonar. Because it takes so much time for sound to go out and back, the robot cannot be moving very fast. Because if the robot is moving fast, right, it's taking a few milliseconds, right? Imagine a robot moving at 80 miles per hour. Sonar is not going to help because it's going to take so much time to tell you and you'll be running over the obstacle before you get that information. So sonar is typically good for slow speeds. So in the US, many trucks use sonar for backing up because that's not high speed. You're going to go slowly back and there's somebody, a kid walks in there or there's an obstacle, it's going to beep, and that's enough time. It will tell you that there's something there. Don't back up because you're going to hit it. So GPS, the original GPS was 1 hertz, not fast enough for cars traveling at 100 miles per hour. So there are 2 types of errors that are interesting because there are errors that are systematic. That means you will get them again. You can recreate the experimental conditions. Those are the errors that you should love because that means it's very predictable. There are errors that are non-deterministic, random. Very hard to debug those because it may happen today, tomorrow it may not happen. So how do you figure out what the effect is? So you typically like the errors to be systematic. So typically these errors have to be described probabilistically. Sometimes they may happen, sometimes they don't. So GPS, right? It doesn't work when there are skyscrapers. But has anybody been able to describe when it won't work? No. So if you go to New York, you have this problem that it's called a multipath phenomenon because the signal doesn't directly go from the satellite to your phone. It's going like this because you can't even see the satellite. You know what I mean? If you have tall buildings, no matter how many satellites they put there, you might not be able to get one directly above. So it gives you the wrong reading of your location. So that is a problem very hard to overcome, the random error. Systematic error is more under control. So we have to use probability distributions. We already saw this, right?
Yeah.
In carbon filtering.
Yeah.
The measurement is given a Gaussian, right? So you have to know what that characteristic is in order to work with it. Encoders. You've seen this already, but I wanted to flash it. Encoders are proprioceptive, right?
Yeah.
You're looking at yourself. Here it is. This is the least sophisticated encoder. Just with one perimeter. See?
Yeah.
So what do they do with these different codes? They have software to draw all kinds of conclusions. If you only have one, right? You can't even tell whether it's going this way or this way. If you just have one pattern around the wheel, you can't tell whether you're going clockwise or counterclockwise, forward or back, because you get the same pulses. But if you put multiples, you can figure out a lot of things. And then you can do checking of the code. because you're reading digital stuff actually. You can read an entire code because this is a code, right? Here, this is actually a digital code. Three channels. So you can do all kinds of things with it. And you see here how complicated it can be. Here's the light source. Here is a mask. I guess the mask is preventing some light from getting through. I'm not sure exactly now why they use the mask. I read it a long time ago. But it's a very complicated encoder wheel. This might be mounted on the shaft of a car. Gray code. Wow. I remember going through a class a long time ago, but all that is faded. I don't remember why they use a gray code. I know that it can get very complicated. That wheel, the encoder wheel, it can be very complicated designs. You probably don't need that for every robot, you know. And I think basically there's no point in going through this. You know, I do this for my class, but also in a reduced fashion. You know, I don't do every one of these because there are more important things to do. And here is LiDAR, see? So this is worth going through. For sound, velocity is 0.3 meters per millisecond, typically. Sound velocity, the speed of sound. For electromagnetic signals, that means light, it's 0.3 millimeters per nanosecond. So a millisecond and a nanosecond. Nanosecond is 10 to the minus 9. Millisecond is 10 to the minus 3. So million difference. So if you give yourself a LiDAR device, you also have to be able to process these kind of return times. You might get 10 nanoseconds. So your electronics has to be very sophisticated to pick up, to be able to read the distance. It has to measure in, you saw that micromouse competition yesterday? Yeah. They already had a problem with respect to the older micromouse competitions. They had to figure out how to read like 3 decimal digits of seconds, right? 1,000th of a second, milliseconds. Here, you have to read nanoseconds in order to use your device. Otherwise, you've got a great device, but you're not using it to the best capacity if you can't measure the time accurately. So T-laser is difficult to measure, and that's why a LiDAR is so expensive compared to sonar, right? That's why the price, is in a completely different range. It's getting cheaper now, though, as they mass produce these. So I just want to point out one thing. So sonar has this particular problem, LiDAR too, right? When you approach an obstacle from an acute angle, it'll bounce off and you won't get anything coming back to the receiver, right?
Yeah.
So you think there's nothing there, and I've seen robots hit that. LiDAR can also have the same problem with glass surfaces. For some reason, you don't get a return pickup for certain kinds of services. That's why Elon Musk insists that cars have to detect obstacles using optical camera. He says we cannot use LiDAR because bad weather as well as glassy surfaces, it almost bounces off at certain angles and you can't tell. So obviously when you design a self-driving car, all these aspects should be extremely researched, well researched, right? Because you can't just say, oh, I'll go with this. And so you have to pour through the physics of it and the advantages and disadvantages and make a decision. So these are the details of how it works. Here's sonars, it's giving you the details of how it works. See, soft surfaces that absorb most of sound energy causes problems. So if you have a soft surface that absorbs sound energy, you won't be able to see it. Yeah. And I think that could be like hanging a cloth, tablecloth on top of the obstacle. Will cause the energy to be soaked in, and it won't bounce back. Surfaces that are not perpendicular to the direction of sound. So if you don't approach them kind of square on, if you go at an acute angle, again, you won't get any energy coming back. Rest of it is pictures, it's got a lot of stuff. Frame rate drops, then the robot has to slow down. Yeah. It's like, you're driving like this, right? Are you watching my eyes? You can't drive that fast. You want the information coming to you at a certain rate based on how fast you're going. So if your sensors are slow, the vehicle slows down, has to slow down. So the frame rate is with all the sensors, right? What frame rate am I getting? So for self-driving cars, that has to be something like 15, 20 frames a second. Maybe it's more, but I vaguely remember it's in the tens. If you don't get that kind of a frame rate, then you're going to collide. Literally it's like driving like this. And some people essentially force themselves into that mode by looking at their cell phone because they're not getting the inputs from the real scene, right? If there's nobody around and you're driving on an empty road, yeah, you can do that. Even then you'll find the car kind of veering if you don't pay attention because the road will push the tires one way or the other. Okay, so we're going to get out of this and maybe we can finish today. Yeah, we can. Yeah, so 30 minutes, I think it should be done. This last part is the most interesting actually. I love talking about that. And as I said, it have some connections to VIT. So let's go to the perception.pdf in your case. I'm bringing up the PPTX. So perception is where, you need to put in the resources because sensors you typically buy and all you have to do is look at the specs and make the right choice. Make sure you don't get random errors, that you know what you're getting in terms of the errors. Alright, so this hub transform, it is such a simple concept, right? But when you first come across it, right, it can be a little bit difficult to understand. So here's what we're trying to do in the context of robots and cars. It has application outside the world of robotics. Look what it has done. So maybe you have a better resolution there, but essentially a sophisticated European style building, the edges have been picked out by the algorithm. So by the way, when I see an object, right, any object, you know how I pick it out against the background? Because I detect the contrast and coloring. So that's how I know there are 5 students in the class because I can tell the contrast and coloring. So that's how the computer algorithms are made to do it. You check for changes in pixel intensity. So images are, in terms of pixels. They are pixel elements. So 512 by 512 means that you have 512 like this and 512 like this. Okay, nowadays we have many more than that. You have HD and 4K and all that, right? So it's much more sophisticated. So, but that's essentially, you're looking for changes in contrast. So edge detection is based on changes of contrast. Until you find the edges, you can't decompose the scene. That's how you see things. The camera is different from you, right? So that's what results in perception, converting the scene into meaning. Okay, so what the hub transform has done is it's identified the edges of the road. It could also be made to identify the yellow stripe if there is one, but I guess he's chosen to only do the edges. Okay, notice there are spots.
Yeah.
It doesn't matter if you've got most of it. Like a human being doesn't get fooled if there is a dashed line and because they didn't paint it recently, it's smudged. A human being can extrapolate through that, right?
Yeah.
So the hub transform also is robust. It is able to produce a result even if there's some missing parts. Okay. So essentially, this technique is useful in identifying structure and image field, just like our eyes do, through picking up lines and other curves which delineate areas of consistency or belonging. See, these lines have meaning, right? There is something consistent about the edges, and something consistent about this, something consistent about the top of the window, the side of the window, right? So the hub transform is going to help you pick it out. Now, the hub transform can also detect curves, quadratic curves. But I've never seen anybody using it for anything other than straight lines. Because the theory is, if you have a curve, it can be approximated by straight lines. And straight lines, there's less competition and it gets the job done. So they do not try to fit, like a quadratic curve. You know what I'm saying? So they are able to get away with just using the base form of the hub transform, which is only straight lines. So objects of interest have boundaries that can be modified or modeled rather with basic curves. Straight line happens to be the simplest and that's what most people use. So the hub transform is insensitive to gaps and boundary. So see, there are gaps, it doesn't care, it gives you like an overall result that is usable. And you can have a little amount of noise, not little, you can have a moderate amount of noise and it will still work. So most images are noisy, right?
Yeah.
There'll be some noise. And so the Huff transform is able to overcome that. And essentially the Huff transform can be used to fill in the gaps. So if you've got the line structure, you can say, okay, it's got to be a line in the middle, and you can draw it out. So the Huff transform result can be filled in with a solid line. And you'll see the students have done that. So here's how it works. You first need to convert the color image into a binary or black and white. Binary, black and white, same thing. Either dark or bright. And that's not difficult because each pixel has an intensity value. So you'll say anything higher than this intensity, I consider it as bright. Anything lower than this, I make it black. So that's called thresholding. So you convert from color to gray level, and then you convert the gray level into a black and white image. And you know how they do that? So because I have an image, this is not a 3D, but I have an image, right? Let's give ourselves something flat. So here's something flat. I'm looking at it as an image. So what I'm doing is I'm calculating the spatial derivative. How much change when I move from one pixel to the other, right? Now, in a uniform background, generally there won't be much of a slope, right? But when you hit the edge of the line, you will get a bump.
Yeah.
And then when you get on the object, no bump, right? It'll be again uniform. Then when you get to the other side, there will be a bump again. Got it?
Yeah.
So that can be used to identify the edges of the object. So our eyes are basically doing that, except that we don't do derivatives. There's something going on in the brain that does the same similar things. But the computer has to be given an algorithm. It can't just say copy this guy. You can't tell the computer go copy this guy because it'll say how, right? So that's what it's doing. It's picking spatial derivatives. Spatial means not with respect to time, but with respect to space. So you can go across the image and say, is there a change? And that's how you pick out the lane lines, or the contrasting spots. So this is the broad understanding of how it works. It attempts to find pixels that roughly align with the edge of the pattern of interest. Most commonly a line is chosen. So this will make no sense to you right now. It will in a few minutes. Each pixel in the image gets a vote. And then you're going to see who gets the highest vote. I know none of this means anything right now. We'll go to the next one. Yeah. So this next two slides are the key. A line is a collection of points in XY space, right? A line is a line. You know, y equals mx plus c. So m is the slope, c is the intercept, right? A line, a collection of points in XY space, can be mapped to a single point in MC space, right? So if I have an MC space, so C and M and Y and X, then any line, what characterizes the line? You have the same M and C. So obviously all of these are going to map to a single point. But how about the other way around? How about a point in XY space? What happens to a point in XY? So this is the image. The image will be in XY space, right? But let's not look at a line. What about a point here? What will it map there? Here's the thing. A point here, any number of lines can be passed through it.
Yeah.
Right? Isn't it true? Any point in XY space, any number of lines can be passed through it. But isn't it also true that the collection of XY points on a line, they all have the same M and C? So the lines anywhere, right? We figured out how to get the lane lines. But lines anywhere, many of them, so that's what was meant by voting. We're going to give each of these pixels a chance to vote for an MNC. And the strongest votes will go to the MNC corresponding to pixels on a line. Does that make sense?
Yeah.
So, let's go to the next slide. So, point here, right? So I take YA equals MXA plus C, and then I write it in the form needed to plot here. So I bring C to one side and say that C is equal to plus YA minus MXA, right? Isn't that a straight line also?
Yeah.
But the slope is what now? It's not M, it's minus XA and YA. So any pixel in XY space maps to a straight line in MC space. So let's go and apply it. Look at this. So that is going to be a feature. It could be the right lane line, right? Look at the votes that this particular MC is getting. This particular MC, why is it getting so many votes? Because pixel 1, point 1, pixel 1, you know, in an image there are only pixels, there are no points, right? So pixel 1 is voting for the same MC, right? Pixel 2 is voting. So what will happen when you do the plot, when you take all these pixels and say, give me your votes, and you represent the voting by brightness in the MC space. Those with the maximum votes will be the brightest, right? That represents that some structure is going on there, right?
Yeah.
That's why so many pixels are voting for the same MC, because you know it's probably a line and all of them have the same MC, so all the pixels on this line are saying, okay, I vote for this guy because I'm on this line. But they do not vote for any other line because there's not much, there's no feature this way. If there was, yeah, you will get votes for a different MNC, right? So let's see what happens here. So we need the most intersections, the brightest intersections resulting from the most intersections. That's the voting. You get a lot of MNC voting. You know why? Because look at this. Look at this.
Yeah.
How many straight lines is extracted, right? But over here, you know, that might be a line, don't you think? That looks like a line to me. The top of the trees.
Yeah.
So how will you pick the ones you want? Because of all those lines that you see, there will be some that are very strong. And maybe the top two will be your lane lines. You can also use heuristics, right? We used the word heuristic earlier in connection with A-star. You can say, I have a structure here, a structure here. It looks like the spacing between that is like a regular lane line on a road. So you say, okay, these must be the lane lines, not something else. Because these are kind of looking like they are in parallel, right?
Yeah.
And they have the spacing that you normally see on a highway. So it's got to be the lane lines. So you can use other arguments to strengthen your conclusion. Okay, this is a minor implementation issue. I'm going to skip it. You know, they don't usually use mx plus c. They use an alternate parametric form of the line. I'll tell you quickly why, right? What happens if a line is vertical? What is its m slope?
90 degrees.
Well, infinity.
Yeah.
So computers have problems with infinity. So they switch to this form of the line, rho and theta. You can look it up. It's a parametric representation of the line. Rho can never be infinity because the image is sitting right here. So the maximum rho is across the image. The maximum rho is across the image, right? And theta, you already know about theta. Theta is finite. So by switching from MC to rho theta, you avoid that problem of implementation. Look at that. So that is an MC image for, I don't have the original pixel image, but look at the brightness. So it's got a lot of structure in it. Maybe I imported this later. See here?
Yeah.
It picks out the lane lines. So this is the MC space, and then this is a half. I don't know what this blue line is. See, it's picked out all the rail lines. Oh, yeah, I think this is the half image. Yeah, those are intermediate steps. You see, it's got all the rail lines. Half transform.
Yeah.
So you pick the bright spots, go with the top one, which is the strongest structure. Maybe you go with the first 5 or 6. You're expecting 5 or 6 railway lines, right? And then you know the spacing of railway lines, so you can double check. You know what I mean? And therefore you got it. See, then you can draw a line. Even remember I told you about noise. It doesn't matter because once you've got the broad part of the structure, you can shoot a line through it, and you're saying, okay, this is the line I'm on, because you know you're here, right? You know because the camera is on you, so you know that this is the line I'm on, and then you can see the junctions like the switching going on. So here I think there's a lot of snow, and he's highlighting some problems when you have a lot of snow on the tracks. But these are advanced studies, so I want to get to the students, the former students of PIT, what they did. So I have a bunch of images here. Let's start with the first one, which they haven't done half yet. So this is a newly painted parking lot. They didn't get it painted. It just so happened that it was painted. So you know that the parking lots have this cement barrier there, and typically there are cars with low clearances. And if you're not watching and you don't have a camera, it'll destroy your fender. Because if you're sleeping and backing up, right, or even sometimes going forward, you can't sense, how far away they are. Some cars have really low clearances, and they can take out your fender. So that's the original image, and then I'll show you another image to give you an idea of the challenge they gave themselves. They were working on a course actually. So freshly painted delineators for the parking spot, and then another one, color picture showing the grass. So by the way, if you have, let's say the grass there's some water here, or maybe it's a hot summer and the grass here is burnt out, that could produce a half-line structure. But what you're saying is that you hope that the other structures dominate. So it'll be like lower level of voting, still a line, but lower level of voting. The thing is this, there's no certainty in the world. So you cannot expect an easy problem where the answer is obvious and it is the 100% correct problem. You have to deal with the world as it is, and you have to write heuristics and test the algorithm in different situations. So they're trying to figure out where that is and tell the driver, okay, it's approaching. So let's see how they succeeded. So this is Melvin and Karthika, who both got their PhDs last year. So this is the half result. Notice, it picks up this intersection between the vertical and the horizontal.
Yeah.
So this has been drawn after the half crossing. It fills in the complete line. It has also caught this edge, right? So right now they're not looking in this direction. They're only looking this way. So you can figure out, so you know that in any image it's possible to calibrate how far a feature is. So once you do that, you can figure out how far this is. That's not a danger, right? Because that is the danger. So maybe this should be a yellow and that can be like red. So this was just a course, right? In order to put it in a car, you have to, So this course was being taught by somebody, an adjunct from the auto industry. So he got them to work on this project. So just 4 images to go and then we quit. So here I picked up the bottom angle here, like this crossover from the vertical to the grass, and it also picked up. See, it made a little bit of mistake here because the line kind of came over. So you can figure out where that is. Pretty good job here too. They were looking for the horizontal first. You can also look for the verticals. So it picked out that edge, which is red, right? That's the dangerous part. This is, if the car gets so far, then you can might as well throw away the car, because the repairs, if the car should be even here, it should stop well short of that. 2 tops here, and a red. So you see that. So there's so much dirt here. The paint has come off. That the half-foot mistake. When you do edge detection, right? I told you spatial derivative. Maybe it sees this as an edge because something's happening here. It's kind of white here, and then it gradually starts to fill out. So maybe it's picking that, but it's not making the high vote count. So even though they show up, they don't make the high vote count. Only these get high votes. These. And do you realize not all 3 of them can be high? Like one has to be the highest, but you pick the top 5. You say, okay, what kind of features am I looking for? How many? And on that basis, you start with the topmost voting, and then you pick a few more, and then you use heuristics to find out whether it makes sense. So we still have 5 minutes, and I wanted to show you something else, because mentioning names without pictures is not giving them credit. So let me show you their pictures. So this is not one of them. This is Dr. Pollock, my colleague, working on this robot. This seems to be like a spider robot, from what I can tell. It's got multiple legs. And it's a bit scary. I guess it's kind of an oral exam or something. But the student was one of our best students. She's originally from Kerala. But she's not the VIT student. So the pictures of the VIT students are coming up now. So we went to a University of Michigan robotics exhibition where they asked us to bring our own robots and demonstrate. So that's Ratish, and this is Professor Santora, who is the youngest now. He's taken over the robotics capstone project. There's Melvin and Kartika. And you can see their robots in the background. These are all our robots. And then last picture is this one, which has Melvin's convoying robots. So his thesis was on platooning robots, like search and rescue, using a new form of communication called LoRa. So you can see that we have 2 jackals and 3 pioneers. And that's Ratish, and that's Nandan over here, and that's our self-driving car. So this is, like a small car that many people in Europe use. It's an, electric vehicle. But in America, you're inviting trouble. If you take that on the roads, you'll have a huge truck next to you, and I don't think it's safe. So basically, we have 2 of them now. It's a self-driving car, Melvin, Ratish, and Professor Santora. And these are all our robots. These were going around for 2 hours in. So you know what it is, right? Convoy. Like there's only one leader, and the others are following. So essentially, the others are automatically following the leader, and the leader is not being led. It's on a path, that is circular. So it could be any path. You can go outdoors, and it's like a rescue mission, right? So the first one will lead the others through. So it's got different modes, whereby if a tree falls between number 3 and number 4, now the 4th cannot see, its leader, which is the next robot. So it becomes the leader itself, and then it starts to go to the goal on its own. Can I give a quick piece of advice? Yeah. So don't focus on the specifics. Writing code is a for loop, or all that will come. But the big picture is where it all begins. You have to understand the thing from 30,000 feet, and only then you can start writing code and so on. So the concepts are the most important, not code. Code will follow or should follow.